Alright, we're going to be looking at 3 questions from homework chapter 14 in some detail because I know a number of students had difficulty with these and we want to look at the appropriate way of solving these types of problems. The first one, number 18, showed some version, I think everyone's numbers were different, but some version of the problem shown here where we have an equilibrium between carbon dioxide, hydrogen, and carbon monoxide and water, all in the gas phase. We had some equilibrium concentrations given to us, and from that we could calculate our initial Kc, the product of product concentrations over the product of reactant concentrations, all raised to the first power because we do not have any other stoichiometry in our chemical equation. Something to make note of here is that we get a Kc at that temperature, and the part B, which was probably the more challenging part of this problem, is not talking about changing the temperature from part A, so we should expect our part B to give us the same overall Kc value as part A. What we see is that in part B we add carbon dioxide to the mixture. As a result, we see here that Le Chatelier's principle tells us that when we add reactant, the system is going to shift to counteract this disturbance. It is going to make more product. So that's just something for us to keep in mind as we go through the calculation. In order to perform this calculation, we set up our ice table with our initial concentrations given to us in part A. We assume that those are the concentrations for all of the species before it has gone in this forward reaction, except carbon dioxide is replaced with this new concentration given to us in part B. We do a minus X in the change column, change row rather, for each of the reactants, and a plus X for each of the products. Once again, if we had some other stoichiometry there, we would put plus 2x or whatever the stoichiometry was, but since all of these entered with a stoichiometry of 1, we have implicit 1s in each case. And then our equilibrium column is simply the sum of the initial plus the change column. We go ahead and plug that back into our Kc that we already solved for in part A. We plug in those values, we expand our multiplication on the side of the equation. We group our powers of x, set everything equal to 0 to get our a, b, and c coefficients to plug into the quadratic equation. I haven't done that here, but I'm going to show a work through of that example for number 27 in case any of you are having difficulty with that, so please stick with these. We will now move on to 25. On 25, we also have an ice table. We're given a chemical reaction once again all stoichiometries of 1 in the balanced chemical equation. We are told initial concentrations. We're not told initial concentrations of products. We'll assume that those were 0. And then we are told our equilibrium concentrations for one of these species. So what I've shown here is I've filled out the ice table already. We have our reactants, our products, our initial amounts of reactants, 0 initial concentration of products, and then how did we get the change column? We went back to that. The information that was given to us was that at equilibrium we had 0.13 moles of CO2. As a result, we could take the difference between the initial and equilibrium and know that that was our change. That is how we got the negative 0.66 in the CO2 column for change row. And as a result, by knowing that that was minus X, NO also should have been minus X, and then NO2 and CO each plus X in our arbitrary ice table, we were allowed to go through and assign this 0.66 value to X without going through and solving for a given Kc as we did in the previous example. Once we have our equilibrium values, we can plug those in appropriately for Kc and get our overall numerical value. Something to make note of there is that even though these were given to us in moles and we don't know the volume of the container that they were in, because of our stoichiometry, it doesn't really matter the volume of the container. Those would cancel. We end up with a unitless Kc anyway. So normally we would like to be working with molarity rather than moles, but in this case we are free to do either. Okay, so our final example from chapter 14 that we want to see was problem 27. We have, in this case, this equilibrium of N2O4 and NO2. We're at a fixed temperature and we're told that the volume is increased by a certain amount. What we need to note is we are at a fixed temperature, we have our equilibrium expression. I wrote it as N2O4 in equilibrium with 2NO2 as the product. If you wrote it the other way, it should still work, but you will get different Kp values. Go ahead and solve our initial Kp and then consider that if the volume is increased by 1.8, this decreases our pressure by 1.8. So the initial pressure of 0.15 atmospheres for NO2, we divide by 1.8 to get 0.0833 atmospheres. Also our initial pressure of N2O4, we divide by 1.8 to get 0.111 atmosphere in this new larger volume container. We go through and set up an ice table with those initial pressures. We give our minus x for how much unknown amount of reactant we will lose in achieving equilibrium, and our plus 2x due to the stoichiometry of this reaction in terms of how much NO2 will be produced. Go ahead, plug that into Kp, remembering that since it's at the same temperature, our Kp is the same value even in this new larger volume container. We go through and group our powers of x, and here I'm showing actually going through all the algebra of grouping the powers of x. And on the back you'll see I even made a few mathematical errors trying to solve this. I didn't write down my C constant appropriately there. It's 0.00554 and so on. We plug that into our quadratic formula. Okay, so I've identified A as the number in front of our x squared, B, the number in front of our x power, and C, the constant, all set equal to 0 in our quadratic equation. We go ahead and plug in. We find two roots, 2x, just as we saw before and we talked about in our example in class of the good and the bad robot. Okay, we see one of these in this case is giving us the 0.01129 is our root that is giving us, our root that is giving us a positive value for N2O4 pressure as well as NO2 pressure. There's showing where I had plugged these into the calculator wrong. Now they're right. We go ahead, plug that back into the Kp expression, and we find 0.1124. If you remember from the previous side, we had 0.1125 for our initial Kp. Certainly we don't even have that many sig figs here, so we have a match. It's always good to check after solving for your quadratic equation. Check and make sure that the two match up as they should once you've chosen the appropriate x and applied that in your equilibrium row of your ice table. In this case it does, and so we can feel more confident that our answer is correct. Hopefully this was helpful to you for Chapter 14 problems. We will do some additional examples from Chapter 15 as well in a separate video.